Hi, in this lecture, I will be talking about one of the simplest quantitative techniques in facility layout studies. It's called Pairwise exchange method. And then I would like to introduce Craft tool, which is an Microsoft Excel based tool, and talk about how we can use that tool to generate layouts, good layouts. Okay. So let's first start with pairwise exchange method. And by the way, Craft also uses pairwise exchange methods. One of the inputs of pairwise exchange methods it is from two distance matrices. Remember, we already learned a qualitative approach in facility layout model, which is called systematic layout planning approach. And we also learned how to use block plan software, which bases on systematic layout planning approach. And systematic layout planning approach doesn't need any initial layout. That's why we call that approach is constructive approach, or we call it constructive algorithm. So that algorithm develops a layout step by step from an empty layout, from nothing. However, pairwise exchange method as well as Craft needs an initial layout. So this approach is an improvement type approach. So, so after we have an initial layout, we can easily generate a distance matrix between every pair of departments because we know where the departments are located at the beginning, right? So this distance matrix is called from to distance matrix. This is one of the inputs we need to have at the beginning. The second and the most important input is the from to flow matrix, which shows the flow between every pair of departments. Remember, in systematic layout planning approach, one of the critical input was the adjacency matrix, which shows the relationship between every pair of departments. And how do we get these relationships? By talking to experts, by talking to foremen, workers, or managers, or even sometimes we can consider the number of trips between them, and using our experience we can come up with qualitative ratings. Here the flow matrix shows the number of trips between every pair of departments. How we can get these number of trips? First, we can take a look at the routes of products, process steps of the processing products, okay? Or we can also use demand information, average demand information, to see how frequently each department will be visited and so on. Okay, so these are the two inputs we need to have. So from two distance matrices and flow matrices, like in this example. In this example, we see that there are 6 departments from A to F, okay? And this is a symmetric distance matrix. That's why in diagonal we don't have anything, okay? So distance from A to B is 18 units, as well from B to A, okay? It may sometimes be asymmetric matrix if distance from A to B is not equal to B to A due to restrictions on the road. You know, in some facilities, some roads are one way. So I can go from A to B using this road. However, to be able to come from B to A, I may need to go around other departments and visit A. Therefore, distance will be different. Okay. However, for now, for the simplicity, we will be considering symmetric matrix. And this is an example of flow matrix. In this flow matrix, we see that from A to B, I make 40 trips every day, every week, or 43 pallets of products are moved from A to B in a day. From D to B, 22 pallets are transported. From B to D, 60 pallets of products are transported in a day. So these numbers actually show or are related to number of trips, number of units moved between every pair of departments. So they are actually a kind of weight. And our goal will be to reduce the total travel distance in a facility. Okay? So for this, we will try to arrange the locations of departments to minimize total traveled distance. How we are going to do that? And before I talk about the approach, so if we have distance metrics and flow metrics, multiplying these two metrics, we can calculate the total travel distance in a given layout. Okay, so if the distance between if from A to B is 18, and if there are 43 trips are made, then the total travel distance from A to B is 43 times 18. Okay, from A to C is 40, the distance from A to C is 26. When I multiply then these two numbers, I will get total travel distance from A to C. So when I do this for every pair of departments and add them up, I will get the total travel distance in a given layout. Okay. So after we multiply those numbers, we get these numbers. Okay. This is called flow cost matrix. And when you add all these numbers up, you can get the cost of a given layout. So now let's talk about pairwise exchange method. As I said before, this is an improvement type algorithm and it needs an initial layout. Okay, this is an heuristic, so it doesn't guarantee an optimal solution. And this is how it works. As you can understand from its name, we are going to switch the locations of every pair of departments and evaluate its cost. Okay, until we don't get any further improvement. So every it will be a kind of algorithm that we search for a good layout from a given initial layout. Okay. Now let me solve an example problem, very simple example problem to make it clear. In this example problem, there are 4 departments. Okay, these rectangular blocks represent the locations of departments, and these departments are going to arrange in a line like an assembly line. Okay, each has an equal area. So suppose that this is the centroid of department 1, 2, and 3, and 4. Okay, and this is the initial layout we have at the beginning. The flow between departments are given like this. Why there is no number right here? In this example problem, we actually accumulated total flows on the upper side of the diagonal. Okay, so this 10 actually consists of flows from 1 to 2 and 2 to 1. Okay, for the simplicity, I accumulated these two flows in one cell, which is 10. So maybe from 2 to 1 we had 7 trips, 1 to 2 3 trips, but when I accumulated them 10 trips occur between 1 and 2. Okay, now this distance matrix is actually kind of between. Okay, so when we look at this flow matrix, we immediately see that between departments 1 and 4 there is a high traffic. Okay, so at the end, actually I would like to see a layout in which departments 1 and 4 are very close to, are adjacent to each other, okay. In the initial layout, however, 1 and 4 are not adjacent to each other. So you can easily see that there will be an improvement when I switch the locations of 1 and 4. However, the algorithm says this, okay? Start from an initial layout and do every possible exchange, and then choose the one that provides the highest savings. To be able to apply the algorithm, I first need to calculate distance matrix, from to distance matrix, right? How I'm going to do that? Suppose that distance between these rectangulars, the distance between the centroids of the consecutive two blocks is 1 unit. 1 unit, okay? So 1 unit between 2 and 3, 1 unit between 3 and 4. If this is true, then distance between 1 and 2 will be 1. Distance between 1 and 3 will be 2. 1 and 4 will be 3. Similarly, distance between 2 and 4 will be 2. Okay? Then we are ready to calculate the cost of this initial layout. So total cost, this is the arrangement of departments. 1 is in the first block, 2 is in the second block, 3 is in the third block, and 4 is in the fourth block. So the initial layout might be different from this one. You may have decided to have this kind of initial layout, right? For instance, this might be a different initial layout. 3, 1, 2, 4. Okay? At that point, from two flow metrics won't change. However, distance metrics will change because now the locations of the departments are different, right? However, so eventually we will be able to calculate the total cost. This is the flow between 1 and 2. And this is the distance between 1 and 2. This is the flow between 1 and 3. And this is the distance between 1 and 3 in the given initial layout. 1 and 4, 1 and 5, I'm sorry, there is no 5, I'm sorry. 2 and 3, 2 flow between 2 and 4, and flow between 3 and 4. When I multiply these flows and distances, we get the cost of the initial layout. In the initial layout, total traveled distance will be 125. So what did I say before? Using this initial layout, and we will do every possible exchange. What are the exchange? What are the pairwise exchange I can do? I can switch the locations of 1 and 2, right? I can do 1 and 2. What else? 1 and 3, 1 and 4, 2, 3, 2, 4, and 3, 4. Because I can switch 1 and 2, it also means that I can switch 2 and 1. That's why I do not repeat it, okay? So in total, there will be, how many departments we have? 4. Okay, 2 combinations of 4 swaps. Okay, now let's take a look at these swaps and see how the costs are calculated. Okay, when I swap 1 and 2, the new layout will look like this. 2 will be here, 1 will be here, 3 will be here, 4 will be here, okay? So the flow doesn't change, however, the distance changes. Distance between 1 and 1 and 3, 1 and 4, 2 and 3, and 2 and 4 will change, okay? So this is the representation of the layout after I swap or I exchange the locations of 1 and 2. And these sequences are still the same. They represent the flows between 1 2, 1 3, 1 4, 1 5, 1 6. Okay, so let me put it right here for the clarification. No, I'm sorry, I made the same mistake again. 2 3, 2 4, and 3 4. So now distance between 1 and 2 is 1. How about 1 and 3? Distance between 1 and 3 is 1. How about 1 and 4? 1, true. How about 2 and 3? 1, 2, right? It was before 1, now it is 2. How about between 3 and 4? Did I make a mistake? 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 2, 4. Okay, this is 2, 4. 1, 2, 3 units, and 3, 4 is 1 unit, okay? But the total cost of this layout is 105. Is it better than before? Yes, it is. It was before 125. Now it is 105. But am I gonna stop? Am I gonna say that this is the best I can get it? No. As I told you before, we will do every possible exchange. The other exchanges are swap, exchange locations of 1 and 3. Using which layout? Using initial layout. So using this layout, I'm going to exchange the locations of 1 and 3, okay? So the new one will look like this. It 1, 2, 3, 4. This was the initial layout. After I exchanged the locations of 1 and 3, 3, 2, 1, 4. Okay? So this is the new sequence. And this is the cost. And when you do the other exchange, these are the costs. So what did I say before? I said that choose the layout that provides the highest savings, which is this. I'm gonna choose this layout. Am I gonna stop? No, I still don't know if this is the best I can get it or not. So I'm gonna go to second iteration. In the second iteration, I am going to start with this layout. Okay, this layout goes to second iteration. So at the beginning of the second iteration, this now is an initial, this becomes an initial layout with a cost of 95. So what I'm gonna do, I'm gonna swap every possible exchange. These exchange, we know these are right. 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, and 3, 4. These exchange will be done on this layout. So for instance, when I exchange 1 and 2, I swap their locations and the new layout looks like 3, 1, 2, 4. Flows do not change. The flows do not change. However, distances changes. This is the distance between 1 and 2. It is 1. This is between 1 and 3. It is 1. This is distance between 1 and 4. 1, 2. Okay? So I keep the same sequence, okay? So now this is the cost of the sequence, the layout 3, 2, 2, 3, 1, 2, 4. So when I do all these possible exchange, I still get an improvement. I decrease the cost from 95 to 90, and this is the best layout among these layouts, okay? So am I gonna stop? No, I'm gonna go further and look for if there is any better layouts or not. In the next iteration, I'm gonna start with this arrangement, okay? This is the arrangement. And I'm gonna do every possible exchange again. As soon as we do the exchange, we will recalculate the distances and multiply with the flows, calculate with the cost, okay? After we calculate cost for every possible exchange, look for if there is any better layout than before. The cost of this layout was 90, so there is no better layout than this 90. So we can say that, hey, this is the best we found so far. Is it optimal? We don't know. We don't know. And as long as we solve it optimally, we can never guarantee that this solution is the best one. Okay, is the optimal one. Actually, when you solve mathematically, we see that this is the global best one. However, again, pairwise exchange method is a heuristic method. It doesn't guarantee optimal solution. Okay, so this is for one. This is a solution for a given one initial layout. So if you want to make sure if this solution is good or not, you can go back and change your initial layout and do all these steps, go through all these iterations and look for if there is any better layout or not. Okay, so this is the end of pairwise exchange method. In the next lecture I will be talking about craft 2. Have a nice day. Take care.